when non-metal oxides, so we've got sulfur dioxide, carbon dioxide, and phosphorus pentoxide that we've just worked on now, dissolve in water, you land up with a weak inorganic acid. So they are going to form an acidic substance. So let's get these three oxides written down: non-metallic oxide, carbon dioxide, sulfur dioxide, phosphorus pentoxide. Carbon dioxide can also be written as carbon 4 oxide, sulfur 4 oxide, phosphorus 5 oxide. That tells you the valency of the carbon, sulfur, and phosphorus respectively. Turns out they're all soluble in water, and our universal indicator is always going to go a yellowish orange color because it's a fairly weak acid. It's not going to go bright red. So the solutions are all going to be acidic, and the acids that are formed are slightly different. You're going to get a balanced equation each time that you need to write. Carbon dioxide, when it dissolves in water, forms an acid called carbonic acid. Sulfur dioxide forms not sulfuric acid, sulfurous acid. And phosphorus pentoxide forms phosphoric acid. The formulas for those are H2CO3, H2SO3, and H3PO4. First, we're going to take a look at a video where we can actually see what happens to the pH of this solution when we put some carbon dioxide into it. So here, first some universal indicator is added to the solution. It's just water. So your universal indicator will be greenish, and greenish indicates that you've got a pH of around 7 or 8, 8 or 9. It's now gone a dark blue color. They've actually added some base to this for greater effect. So it's now a basic solution. Guys, just dropped some dry ice, which is solid carbon dioxide, into that solution. Watch the solution. It's going a lighter and lighter yellow. It's going to turn to green, and then it's going to go yellowish. There we go, yellow-orange color. And that is because of the carbon dioxide dissolving in the water. Here we are now going to react some sulfur dioxide. So I'm heating up sulfur powder, and the sulfur powder is reacting with the oxygen in the air, and so I'm making some sulfur dioxide in this test tube. When I put some litmus paper there, I am going to get, it's going to turn red. So this is red litmus paper. If I put it at the mouth, it remains red. That means I've got an acid. And if I put blue litmus paper there, I will actually see it turning red in color. The acid that's being formed is sulfurous acid. So sulfur dioxide and water form sulfurous acid. Carbon dioxide and water forms carbonic acid. Now those two acids are responsible for acid rain. When we burn coal in industry, we burn in carbon and sulfur. So we land up forming carbon dioxide and sulfur dioxide. When it rains, they dissolve in water and they form carbonic acid and sulfurous acid. Those two acids then go and they cause the problems that are associated with acid rain, such as changes in pH of soil and pH of water bodies like rivers and lakes and dams and all of that sort of thing. They also cause building damage, and they also cause damage to plants. So the actual acid falling on the plants causes damage as well. So acid rain is a major pollutant. It's important to realize that acid rain has got absolutely nothing to do with the ozone. It's got absolutely nothing to do with global warming, or not quite nothing, but very little. It's a separate situation to global warming. It turns out that carbon dioxide and sulfur dioxide are also both greenhouse gases, and therefore they also contribute to global warming. But that's totally different. When you're talking about acid rain, you must not talk about global warming. You're talking about these two gases dissolving in water to form two acids, and acids upset the environment for plants and water-living animals. They cause damage to plants and to buildings, and that is the problem with acid rain. Phosphorus pentoxide, when water is put onto it, actually is a highly exothermic reaction and forms some phosphoric acid in the process.